Let's do this problem right here. The question is asking find eigenvalues, the first question. So to do that, I have to set this one into determinant of a minus lambda I equal to 0. So if I calculate this one, so determinant a means this matrix right here, and lambda I identity of this 2 by 2. So it's going to be 1 1 0 0. So that's the identity. So if I multiply the identity, I will have lambda in these two corners. So if I subtract this one a from this one, I will have 1 minus lambda 2 4 minus lambda, that is equal to 0. And if I find determinant of this one, that's going to be AD minus BC. This is going to be 1 minus lambda multiplied by 4 minus lambda, that's AD, and minus BC is going to be 2 times 2, so this is going to be minus 4 equal to 0. And if I multiply this one, 1 times 4 is going to be 4, and 1 time minus lambda is going to be minus lambda times 4 minus 4 lambda, and the last one is going to be minus lambda times minus lambda is going to be plus lambda square. Minus 4 equal to 0. From this one we can cancel 4 and minus 4, and if I rearrange this one, this is going to be lambda square, and minus lambda minus 4 lambda is going to be minus 5 lambda equal to 0. And I can take the lambda common to factorize this one. So if I take the lambda common, this is going to be lambda minus 5. Therefore the lambdas are going to be lambda is equal to 0 and lambda is equal to 5. So these are the two eigenvalues. And the next questions are asking find the eigenvectors. To find the eigenvectors, we have to set this one into null space. A minus lambda I equal to 0, that's the null space of this one. And we know A minus lambda I is this pattern. We found it already. So we can put the same thing right here. So it's going to be 1 minus lambda 2 4 minus lambda, that's equal to 0 0. Then what I have to do, I have to plug this value. So first I am taking lambda is equal to 0. If I take lambda is equal to 0, if I plug this 0 right here, it doesn't change the equation. So I can write the same matrix right here. So it's going to be 1 2 2 4 0 0. And if you notice that second row is multiplication of the first row, so I can simply eliminate this one by multiplying the first row by -2 and adding to the second row. So let's do that. So it's going to be 1 2 0, and if I multiply the first row by -2, it's going to be -2 r1 plus r2, which will give us 0 0 right here, and the other one is going to be also 0. So from this one, this is already in the Gauss-Jordan pattern. Now I can form the equation for this one. That's going to be x plus 2y is equal to 0, and we know y is our free variable because the first column has pivot, the second column doesn't have pivot, so that's going to be the free variable. So this is y is free variable. So we have to write every answer in terms of free variable. So first x is going to be equal to minus 2y. Therefore I can write this answer as, so this is going to be eigenvector, right? So eigenvector is equal to minus 2y, that's my x, and y is going to be y because it's a free variable. And if I take the y common, this is going to be minus 2 comma 1, and if I can write this one as span of, when I write the span I have to eliminate this y because y mean it can be any real number, so we want the simplest form when we write the span. So that's going to be minus 2 1, and this is the eigenvector of the first eigenvalue. Now we have to find the eigenvalue for this eigenvector for the second eigenvalue. To do that one, I have to take the lambda is equal to 5 and plug this one into this equation. So it's going to be 1 minus 5 is going to be minus 4, and 2 is going to remain the same. Then bottom 2 also remains the same. 4 minus 5 is going to be minus 1. And if you notice, if I multiply the second row by 2 and add it to the first row, it will become 0. So I can flip the second row into first row because second row is much simpler. So if I flip that one, it will make the solution much easier. So 2 minus 1 0 is going to be the first row. Second row is minus 4. I can also, so let's write it one more step. So 1 minus 4 2 0. And if I want to eliminate this one, I can multiply the first equation by negative plus 2 and add it to the second equation. So if I do that, let's see what I get. 2 minus 1 0 and 2 r1 plus r2, which will give us 0 0 right here. And I am not fully solved into Gauss-Jordan pattern. To make this Gauss-Jordan pattern, I have to divide this by 2. So if I divide this by 2, it's going to be 1 minus 1 over 2, and the other side is going to be 0, and bottom is going to be 0 0 0. From this one I can solve this equation. This is going to be x minus half y is equal to 0, and we know that y is free variable because y column doesn't have a pivot, therefore this is our free variable. Y is free variable, therefore x is equal to half y. From this one we can write the answer for the eigenvectors. So eigenvectors are going to be, eigenvectors is equal to half y comma y, and if I take y common, this is going to be half comma 1, and we can write this one as span of half comma 1. And also I can write this eigenvector as 1 comma 2 because eigenvector like this span, you can write any multiplication, because if I take 1 comma 2, it makes the next questions much easier to calculate other things. So I take the span of 1 comma 2. So that's the eigenvector for the second one. And the third one is asking find the basis for each eigenspace. Basis is going to be these two values. So C question. So C questions answer is first for the lambda is equal to 0. The basis is going to be equal to this one, minus 2 comma 1. And for lambda is equal to 5, the basis is going to be equal to 1 comma 2. And this is the answer for the C question. And the D question is asking find algebraic and geometric multiplicities of each eigenvalue. And to find this one, we have to check this one. If you see the power of this one, that's what determines the algebraic multiplication. If you see both of them have power of 1. So both of them have algebraic multiplicity of 1. And geometric multiplicity depends on the free variables. So we already found out for lambda is equal to 0, we have one free variable, that's y. For lambda is equal to 5, we have also one free variable, that's y. So both of them have equal geometric multiplicity, that's 1. So the next question is asking, is A a diagonalizable matrix? The answer is yes, because if we have equal number of algebraic multiplicity and geometric multiplicity for each eigenvalues, that means that's diagonalizable. So the answer is yes. The next question is asking find matrices P and D such that P inverse AB is equal to D. So to find the P, what we have to do, we have to arrange this basis we have found here in a column space. So if I do that, it's going to be minus 2 1, and the other one is going to be 1 2. So this is my this is my P value. Then D is going to depend on this one. So if we write minus 2 1 in the first column, we have to follow the same pattern for D. For D, the first value is going to be 0 because I took the lambda is equal to 0 vectors for the first P value, so I have to choose a 0 for the first D value. Then the second value is going to be 5 because I chose the lambda is equal to 5 as the second vector, so this is going to be 5, and the others are going to be 0. And what happens if you switch this around? Like if you write 1 2 in the first column, you have to write the first 5 in the first column. So you have to follow the order of the way you are writing the answer. And that's how we find the P and D, and that's what they are asking, right? Find P and D and P inverse P. The next question is asking find A20. So to find the A20, I had to use the equation that's A is equal to PDP inverse. A is equal to PDP inverse, and if A has a power, for example, in this case we have A power 20. So A power 20 is going to be P power D, P times D power 20 P inverse. And to make this calculation easier, one more thing we can do, we can make this basis into a orthonormal basis. This is already orthogonal, but to make this one orthonormal, what we have to do, we have to divide this one by its magnitude. So in this case, for the lambda is equal to 0, the magnitude is going to be minus 2 square, so it's going to be 4, and the other one is going to be 1 square, so 2 square, 4 plus 1 square root, so it's going to be 5, root 5. So if you divide everything by root 5, you will get orthonormal basis. And if you find the orthonormal basis, according to this rule, so P inverse of the orthonormal basis is going to be P transpose. So if you transpose the orthonormal basis, you will get the P inverse so easily. You don't have to do Gauss Jordan or anything to calculate the A inverse, P inverse. So you don't have to do that will make everything easier, right? So in this case, what I can do, I can take this orthonormal basis and write this one as also. Let's see. So a power 20 and P. So instead of P, I am copying this orthonormal basis. So if I take this orthonormal basis, the first column is going to be minus 2 over root 5 over 1 over root 5, and the other one is going to be 1 over root 5 over 2 over root 5. So this is my P, and D is going to be simply 0, 0, 0, and we have to power this 0 power 20 is going to be 0, and 5 power 20. So that's going to be my D. For the P inverse, it's going to be the transpose of this P. So transpose comes out to be same thing, because I have to just rotate the column into the row, and so first column is going to be first row, and second column is going to be my second row. So if you rotate, it's going to be same thing for this pattern. So it's going to be minus 2 over root 5, 1 over root 5, 1 over root 5, 2 over root 5, and that's the final answer. We can't simplify this one because it's a big number. If you leave it as like this, that's okay, and that's the final answer. I hope you guys like this video. See you next time.